I think p-n junction diodes are as common as any device that you take. They're interesting in themselves, right? And p-n junctions are part of almost every device. They're part of LEDs, solar cells, bipolar transistors, MOSFETs. p-n junctions are everywhere, right? And when you read p-n junction, the first thing that you encounter, one of the first things that you encounter is the concept of cut-in voltage. So the question that I'm raising is cut-in voltage of a diode an illusion? Is it an illusion? So what I'm claiming is there is no cut-in voltage. There is no cut-in voltage of a diode. It's all an illusion, right? All right, so what do I mean by that? Okay. Let me start. So I'm going to do some bashing of the books, right? The traditional books that are there, I'm going to bash them up. I'm going to tell that they are wrong or they're doing things wrong, okay? Okay, here, let me bash up Millman, right? So Millman's, you read the Millman and Grable, you read the chapter on diodes, you have a long discussion of diodes. Let me highlight what he says. So he's drawing, I've taken apart and blown it up. So he's drawn this current voltage characteristics, right? And note what he's saying. A noteworthy feature of this characteristics is the existence of a cut-in, offset, or turn-on voltage V gamma, below which the current is small, and beyond V gamma, the current increases rapidly. Right? So what he's saying is there is a special voltage in my diode. There's a special voltage, some unique point in my diode described by V gamma, below which current is very, very small. Nothing interesting is happening. Above it, exponential increase. It's sharply increasing. So as I said, people who know diode will, of course, know much more about the diode. But, a simple introduction, when you read about it, you'll say, there must be something special at V gamma. There must be some specific, something special is happening at V gamma. That below it, current is so small, above it, just rises dramatically. And therefore, V gamma cut-in voltage is so important. Is this the only book talking about it? Well, read this. The physical implication of this cut-in voltage is that below this voltage, the diode carries negligible amount of forward current. And for voltages above V gamma, the forward current increases significantly. I just wrote book 2. I didn't want to bash them up, okay? I didn't want to explicitly write who's saying it. Okay, book 2. Book 3. Note that the current is negligibly small up to 0.6 volt and rises sharply beyond that, as I said. So all of you are saying something magical is happening at 0.6. Something magical is happening at 0.6, it rises sharply. Below that, nothing. Very little current. All right, so here is the diode's characteristics. Right, these are measured characteristics. I took a diode, I asked my students to measure it. These are measured characteristics of a diode, of a particular diode. So I asked the students, what is the cut-in voltage? All of them will say 0.6, right? It's obvious. Current is sort of negligible and then rises sharply at 0.6, right? Cut-in voltage is 0.6. No problem. I show them another diode's characteristics, another measured diode characteristics. And I ask them, what is the cut-in voltage here? They say, sir, cut-in voltage is 0.3. So they say, sir, that must be the silicon diode, 0.6. This must be the germanium diode, 0.3. Right? That must be the silicon diode. They've all read that. This must be the germanium diode, 0.2 or 0.3. And then what I put them side by side, and I tell them, both are the IV characteristics of the same diode, 1N4007. It's the same diode. Same diode, right? So they were thinking silicon diode, 0.6, germanium diode. These are the characteristics of the same diode. Is there a unique point where current is increasing sharply? Is increasing sharply, it appears to be here, right? It also appears to be sharply at 0.3. What is the difference? The scale. Here, I put a scale from 0 to 100 milliamperes. And so it appears to be rising sharply at 0.6. I put a different scale, 0 to 0.1 milliampere. It appears to rise sharply at 0.3. There is no unique point. There is no unique point in a diode at which the current increases sharply. There's nothing like that. There's no magical voltage at which the current increases sharply. There's nothing like that at all. It's all a question of, it's an illusion. If you take the diode's characteristics and you plot it on a semi-log, log here and linear here, you find there's no special point anywhere. Do you see any special point? There's no special point anywhere. The current is exponential throughout. The current is an exponential characteristic. It's increasing exponentially here. It's increasing exponentially here. It's increasing exponentially here. It's increasing exponentially here. It's increasing exponentially everywhere. At what point are you saying that current is not exponential and suddenly it becomes exponential? There's nothing like that. All of you know it. The current is exponential throughout. So what is happening is the following. When you say, if I say current below a milliampere is negligible, then I will get a cut in voltage of 0.6. If I say current below a microamperes is negligible, it depends on what you consider as negligible. What scale you want to look at. Different scales will give you, if you plot the characteristics on different scales, it will give you different cut in voltage. It's all a matter of what you consider as negligible and what you consider as significant. If I take a diode for a rectifier, significant current may be 100 milliamperes, 1 ampere. If I look at the base current of a bipolar transistor, the significant current is 10 microamperes. What is significant and what is not significant is depends on what you're looking at, what application is there, right? So you can't just say, so my point is, if you take an exponential characteristics, and you plot it on a linear scale, it gives you the illusion that there's something dramatic is happening at a certain voltage. It's an illusion that occurs when you take an exponential and you plot it on a linear scale. It appears as if there is something dramatic happening at 0.6. In fact, why exponential? Any sharply varying characteristics, if you take and you plot it on a linear scale, it would appear as if there's a cut in voltage. Any sharply varying characteristics. You can take, I'll give you examples here. So the point is, the illusion is clearly seen when characteristics are plotted on a logarithmic current scale. You see that there is no special point inside my diode. And, if you go and read a textbook on here, so all of you can do this. Take this equation. It's an exponential equation. Go into Excel and plot it. Take this equation, plot it in Excel, right? If you plot it on a scale from 0 to 10 milliamperes, it would appear there's something special happening here. If you plot it on a different scale, let's say a 10 microampere scale, it would appear something special is happening here. There's no special anything. It's just an ordinary exponential expression. Ordinary exponential expression, there is no cut in voltage inside my expression. There's no cut in voltage at all. It's just a matter of scale. If you look at an exponential on a linear scale, it appears as sharply rising at some point. There is no unique point called cut in voltage. You go and read a semiconductor book, device book. Take this book here, right? Pick up Z's book, Physics of Semiconductors, right? Start reading the chapter on p-n junction. You will not find any place where he talks about an expression for cut in voltage, a model for cut in voltage. It's not there. It's just, I'm looking at an application over a certain current scale. If I plot it, it appears as if it's sharply rising at that particular point. There is no cut in voltage inside the diode, okay? All right, so an exponential curve viewed on a linear scale leads to the misconception about the nature of the characteristics. That as if something exists, something dramatic is happening at a cut in voltage. There is a unique voltage called cut in voltage here. And this misconception is happening very, very early. It happens very early. How early? This is a plot from class 12th physics book. Class 12th physics book, look what they're writing. Look what they're writing. The current first increases very slowly. The current first increases very slowly. What do you mean? The current is always increasing exponentially. The current first increases very slowly, almost negligibly, till the voltage across the diode crosses a certain value. After the characteristic voltage, the diode current increases significantly. After the cut-in voltage, the diode current increases significantly, and in the bracket they're writing exponentially. As if after the cut-in voltage, the characteristics becomes exponential. It's exponential throughout. In class 12th book, they're writing this. So this misconception is forming very early. That, after the cut-in voltage, the current increases sharply and exponentially. Below that, it's as if there's nothing. We all know it's an exponential characteristic throughout. So right at that particular point where a young student cannot, understand or question, he or she is being taught this, that there is a magical voltage called cut-in voltage. And the students carry that throughout. Now, what is very interesting is this. As I said, if you go and read this book, you'll not find cut-in voltage anywhere in the chapter on p-n junction. If it's such an important voltage, a voltage at which something dramatic occurs, this guy will be talking about cut-in voltage, right? Read this book. No mention of cut-in voltage at all. No mention at all of cut-in voltage. It's not there, okay? Now, cut-in voltage is not really there. But what is really there in a p-n junction? The built-in voltage. Now, something strange occurs. We keep teaching, students keep learning that there's a cut-in voltage. And they also learn about built-in voltage. And over about 25 years, I've interviewed students, and a lot of them will say, sir, cut-in voltage is the built-in voltage. Built-in voltage is there in all textbooks. They talk about it, expressions are there. There's nothing about cut-in voltage. But we keep saying that there's a point at which current increases sharply. So this is, sir, cut-in voltage is the built-in voltage. Right? And we know how wrong this is. Built-in voltage is, the diode operates almost all the time below built-in voltage. We never exceed the built-in voltage. All right? So cut-in voltage or whatever it is much below the built-in voltage here. And if you're thinking it's only students who form this misconception, again, I'll not take the book. Read this book here. Read this book. This is taken from a book here. Even books have started talking about. I looked at YouTube lectures, and they're famous lecturers. They keep on talking about, oh, there is this cut-in voltage, and cut-in voltage is equal to the built-in voltage. What are they talking about? Well, the current is almost zero below V0. For Vf greater than V0, the potential barrier at the junction completely disappears. The potential barrier at the junction completely disappears. So they have taken cut-in voltage and they have merged it with the built-in voltage. Right? Built-in voltage. And they're saying that it's obvious, a young student or whatever is not thinking enough. It sort of makes sense, right? That you are saying that there is a point at which the current dramatically increases. Then you are saying, well, inside the junction, there is a barrier. There's a barrier potential, and which affects the current. So it's natural to put it together. Yes, maybe if I apply a voltage which is larger than the barrier potential, after that the current increases. So the students many times put the two together. This faculty or this person who's written a book has written a book about it also. That the current begins to increase only after you apply a voltage which is larger than the barrier here. All right? So my point before I end this is there is no cut-in voltage, as I said. There is no cut-in voltage of a diode. It's an illusion that occurs when you plot an exponential characteristics on a linear scale. It appears as if there is something there in the diode at which the current increases dramatically. There is no such thing in a diode. And your illusion will be blown away if you simply take the exponential characteristics, plot it on a semi-log. Semi-log plot, you don't see any special point inside a diode at which anything dramatic is occurring. Okay? So there's no cut in voltage.